We are now going to talk about sampling techniques. There are two ways we can do our sampling, selecting the members of the population, and that is we can do our sampling with or without replacement. Okay, so those are the two valid sampling schemes. Now, what is the difference, or what are the similarities? Well, the difference between the two, the similarity is that they're both going to be random samples, but the difference between them is that in one case, sampling with replacement, when you select a member of the population, you put them back into the pool and they have an opportunity or another chance of being selected. So that's in essence what that is, sampling with replacement. So what that means is, in effect, the elements or the members of the population stand more than one chance of being selected. Whereas the case with sampling without replacement, the members or subjects, elements, objects are not afforded a second opportunity. So once they are selected, they are set aside and they are not put back into the pool of possible selections. So they have at most one chance of being selected. Both of these are probability samples, so it's just how the sampling is done. Now, when it comes to sampling, I just mentioned the word probability sample. There are two types of sampling in all, and these are the two types. We have probability and non-probability samples. So what is a probability sample? In a probability sample, sampling is done in such a way so that every element, every subject in the population has a chance of being selected. Notice here I have italicized bold. It has a chance. It doesn't say equal chance, but it simply has a chance of being selected. Okay, so that's what that is. The non-probability samples are those that are not probability, complement of the one above. In other words, not all members of the population have or stand a chance of being selected. Now think about it this way. Let's say a survey is being done in the Mall of America. Okay, Mall of America in Minnesota. Well, none of us possibly has a chance of participating in that survey. So if that survey tries to draw inferences to the entire population of the US, including those who live in California, then that would be invalid conclusions. But if its intent is that mall survey, if its intent is to get opinion about of people about something for those who go to that mall, then that would be perfectly valid. So it's what matters is who's really your target population for these things to work out appropriately the way they're intended to. So I have example of these mall surveys, anecdotal surveys, and telephone surveys. Okay, so these are not probability samples. Any sample that's drawn this way is not probability. So again, the consequence is what I have here. You can only draw inferences if a sample is a probability sample. Otherwise, it cannot be done in a legitimate way. You cannot generalize the results to the entire population. And we are only considering probability samples in this course and in practice also. Nobody wants to have a biased sample. Okay, now when it comes to probability samples, we're going to take a look at, I believe, 4 of them, and we're going to look at 4 of these. First is the one that's the most common one, the one that you're probably thinking of. And I just want to point out also, all of these samples that we're about to see, these are all random samples. So if somebody says, oh, just take a random sample, in public and in layman's term, this is what they have in mind when they say take a random sample. They're talking about a simple random probability sample, okay, or SRS for short, simple random sample. In a simple random sample, this is a sampling technique where every member, every element, every subject in the population has equal chance of being selected. So there you go. The emphasis is on the word equal here. Equal probability of selection. And not only every element, but every sample also. So you have the best of both worlds. You have every member has equal chance, and every sample has equal chance of being selected. Okay. Now, how do we select such a sample? You can use softwares, or you can use table of random numbers to make the selection. Okay, and there are extensive tables in the back of statistics textbooks that actually can be used in order to do this. Since we're not going to do any sampling in this course, so we're just going to skip this part. But going forward, this is going to be our the default sampling technique in our course going forward. All the formulas that we are about to see in the future assume that we have a simple random sample. Okay, that is the sample that's stated up here. Usually, if you don't have a simple random sample and other sample like systematic and so on and so forth, the estimate of standard deviations have to be done differently. Okay, the next sampling method is systematic random probability sample. A lot of people call this just a systematic random sample. Okay, now in a systematic random sample, you have a starting location, a random location, and thereafter you select every kth element. That's what makes it systematic. So here I have an example to show you how this is done. Okay, so in this example, let's say we have 1,000 records on the shelf. Suppose you go to a veterinary office, and there are 1,000 pet files on the record. Okay, and you want to know what is the average bill, the average vet bill, okay, in that location. So there are 1,000 records, and I want to choose a sample of 20 records, 20 files. Okay, so how are we going to do this using systematic? We're going to use a random location. So I just picked the number 162. You can choose the day of the date, the month of the date, or the year of the date. You can ask somebody to just call out a number, any number, just make it up. You can look at the page of a book and pick a number. However is random. So here I just picked 162. You can pick the time of the day. Like for example, if the time is 8:55, then you can say, okay, 55 is my starting point. So once you have your starting point, then that makes up your first records. Now thereafter, how do I make up my sample? You divide the population size, 1,000, by the sample size. This gives you the location of all the subsequent records. So you start with 162nd record, and thereafter you choose every 50th record or file or folder. So the next one, 50 plus 162 is 212. 50 more, 50 more, 50 more, and so on. Now, if you reach the end of the case file, let's say, and you still have not collected a sample of size 20, maybe somebody starts in location 990. That's my starting point. And when I add 50, well, 990 plus 50 is 1,040, but there are only 1,000 records. In that case, it makes sense to scroll in the front of the list and choose case number 40. Okay, so that's how systematic is done. Very easy, very convenient. It works really well in the field, but I have just a word of caution here. Usually for data that exhibits seasonality, such as soft drink sales, airline passengers over time, excluding, let's say, 2020 because of the COVID. But in general, any data that exhibits seasonalities, for example, retail sales are highly seasonal. Things of that nature, we tend not to use systematic. In those cases, the best bet is a simple random sample. And you can kind of see why. Here I have a secular trend, and the way every kth works is that I'm always picking picking here the tops of each wave. You see that? And in this one, where I have some kind of a sinusoidal wave, right, like a cosine or a sine, you have pronounced seasonality in this one. If you start the location here, every case you end up picking up the same point in time. So with this sketch, I'm missing all the peaks and the valleys throughout this process. So that's when we do not use systematic. The next random sample, probability sample, is cluster. So here's an example of cluster random sample. In a cluster random sample, we divide the population into subgroups. So this is a hypothetical population, and I'm dividing it into 1, 2, 3, 4, 5, 6 groups. Now notice the colors I've used here, by the way. If you note, every subgroup has the same color composition. So for example, I have blue, red, green, and so on, blue, red, green in every one of them. So what this is supposed to portray is that all of the subgroups are alike inside. See, you got, for example, this could be County of San Diego, this is County of Los Angeles. Pretty much the diversity is the same in San Diego as opposed to Los Angeles or Orange County and so on. Okay, so in a cluster random sample, the subgroups are homogeneous, meaning alike. But within each subgroup, notice you have so many different colors. So there is heterogeneity within each subgroup. Okay. So inside they are different, but between them they're alike. So what happens is that you can choose one subgroup at random. If you can do 2 or 3, that's fine. The more the better. But if not, you pick one subgroup at random, and then you conduct a census, complete census within the subgroups. Okay, so this is how the cluster is done. So for example, if I want to know the price of a house in a given zip code, so this could be, let's say, 92122, whatever, 92135, 92122, any zip code you can think of. This could be one particular zip code, and then within the zip code you have city blocks. And then I'm going to pick this city block here that's maybe adjacent to some location. Again, all of these are done by random selection. So if I have 1, 2, 3, 4, 5, 6 subgroups, I'm going to choose a random number between 1 and 6. And that's how I select my subgroup. So these become city blocks within a zip code. And then in that city block, you're going to look at the, let's say, home prices in that city block. On that block, every home in the block, you're going to look at the prices. Okay. The next one is stratified random probability sample. Now with the stratified, if you notice, I start with the population just like I did up here. Now if you look at the colors, look how different the colors are now. Inside the subgroups, I don't have all these different colors. Each subgroup has its own color. So what this suggests is this: the subgroups are heterogeneous. Means there's a difference from here to here to here to here and so on. Okay. Now the groups, the collective groups, if there's 2 or more groups, we call these a strata, which is the plural of the word stratum. Each subgroup they refer to as a stratum. So from left to right, I have a stratum number 1, a stratum number 2, and so on. The singular version of the word. Now, because subgroups are heterogeneous, notice different colors means different, truly different here. Therefore, we need representation from every subgroup, don't we? I cannot just say, for example, use the red group here and do a census of them, because their opinion, their taste for the food, their shopping preferences may be different than these. These could be age groups. They're not necessarily people of color. So this could be group, let's say 20 to 25, 25-30, 30-35, 35-40, 40 plus. And if I'm looking at the net worth of individuals in that community, then I don't want to look at the net worth of all the people that are over the age of 45 or 50 here, and they represent the younger generation. So for that reason, we need to have selection from every subgroups. So the subgroups now, within subgroups, they are homogeneous. That's what I have here. They're homogeneous, means alike, alike, alike. So here in the middle, let's say these are all the 25 to 30 or 30 to 40 years old. These are all the ones in that age category and so on. And then what we do is we choose a simple random sample from each subgroup. So I have an example here. I have divided this hypothetical population into 4 strata. And I want a sample of size 400. See down here? I want to choose a sample of size 400 from these 4 subgroups. One thing I will not do, I will not pick 100, 100, 100, 100. The reason, in the first stratum, there are 1,000 subjects. The second stratum has 2,000, 3,000, 4,000 as you go on. So notice there's twice as many people or as many subjects or items in the second subgroup as it is in the first group. 3 times as many in the third as it is in the first, 4 times as many, and so on. So if you look at the sum of the subgroups, the population size in this case is going to be what? 10,000. That's 4 plus 3 plus 2 plus 1,000 makes 10,000. So how are we going to do this? Well, it makes sense that the size of the subgroup here has a say-so as far as how we choose the sample. And in fact, it does. So for the first stratum, the first partial sample size from the first stratum, you divide the stratum size, 1,000, to the total size of all strata, in this case 10,000. And then multiply by the sample size, overall sample size of 400. So that's 1,000 out of 10,000 means 10%, doesn't it? And it makes sense. 10% of your sample should come from this people, from this subgroup. And then twice as many should come from here, 3 times as many from here, 4 times as many here. And that's pretty much how it works out. Twice, 3 times, 4 times as many, and detailed formulas here. So the sum of individual samples here you have for all I, means here I, subscript I means the index. 1, 2, 3, 4 means first, second, third, fourth subgroup or stratum. So there you go. If you add up all the numbers, I get 400. Sometimes you may get into rounding issues. You just have to compromise, offset a little bit. But in this case, there is no rounding. Everything worked out perfectly. So each subsample is selected using proportional allocation method. This is what we did. A proportion means a fraction. There you go. This is a proportion. So each subgroup, the samples from subgroup, is selected using proportional allocation method. Okay, and there you go. Now, let's actually take a look at an exercise here. So we're going to set up this exercise first, and then we're going to solve this, of course, using Megastat. Okay, so let's take a look at this exercise first. In this example, this is from your book, by the way, the problem reads: Majesty Video Production Inc. wants the mean length of its advertisements to be 30 seconds. Assume the distribution of ad length follows the normal distribution with a population deviation of 2 seconds. Okay, suppose we select a sample of 16 ads produced by Majesty. What can we say about the shape of the distribution of the sample mean times? Okay, so remember, they want the mean length to be 30 seconds. So that's the mu, okay? The population mean. Okay, so let's begin with part A. Okay, now in part A, because we were told that the length of advertisements follow a normal distribution, right? We were told that in the second line right in here. The distribution of ad length follows a normal distribution. Because we're sampling from a normal population, therefore the distribution of sample mean will also be normal. So in part A, we can say that what can we say about the shape? The shape is going to be normal. And in fact, let's go a step further and actually draw this, what's going on with this example. So in this exercise, here is a normal distribution. This is the distribution of the parent population, okay, which is normal. The random variable is x. The center of the distribution is where the mean of that variable is believed to be 30 seconds, and we were told its deviation is 2 seconds. Now, they've taken a sample of size 16 from this population. Remember, repeated samples of the same size. The theoretical distribution is going to look like this. This is the mean of x bar, will be exactly the same as the mean of the parent population. It's sigma of x bar, notice the subscript for the variable that I'm looking at, is going to be sigma over root n, the standard error of the mean. That's going to be 2 over square root of 16. Now, square root of 16 is 4, so this quantity is going to be 0.5. Okay, so we are actually working with this distribution, not the one above. We're working with the one below when we go to in Megastat, when we go to actually do this exercise. So here's part A again. Hope you're okay with that part. What can we say about the shape? The shape is normal, and again with those parameters. In part B, we want to know what is the standard error of the mean time. Standard error of the mean, that's sigma x bar, is sigma over root n, and sigma is 2, and square root of 16 is 4. Again, this would be 1/2 second. That's the standard deviation or standard error of the mean. In part C, what percent of the sample means will be greater than 31.25 seconds? Part D, 20.25 seconds. In part E, what percent greater than 28.25 but less than 31.25? So I'm just going to write these probabilities down for part C. What percentage of, notice we are making probability statements about x bar, not x. In chapter 7 we did it on x, now we're doing it for x bar. In part D, probability of x bar greater than 28.25. And again, I'm not going to show you details of this because we go to Megastat, but ordinarily if we were to do this by hand, I would have to standardize the variable, subtract the mean, divide by deviation, create a z-score, go to a table in the back of the book, and all of that stuff. But again, since we use software, we're not going to do that. So in part E, probability that's more than 28.25 but less than 31.25. Now note here, I just put equality. Remember, the probability at a point is 0, so whether you include or exclude doesn't matter. Okay, and the idea here is that no ad is going to take exactly 28.25 seconds. It's impossible if it's a measured quantity, which time is measured. So it's impossible for an ad to last exactly 28.25. If we round it to the nearest 100 seconds, maybe, but if you let those trailing decimals to infinity to roll around, the idea of continuity of time, then it's impossible to get exactly 28.25. Okay, so now we want to find these probabilities, right? So I'm just going to pause this video and go bring up Megastat, and we'll do all three of these in Megastat. Now when we go to megastat, remember, we're going to go looking at this distribution below. We're going to go with a mean of 30, deviation of 0.5. The most common error or mistake is to use sigma 2 in our computations when we go to megastat. But this is about x bar, so we got to make sure we use sigma of x bar. Okay, so here we go. Okay, so here I am in Excel and I have megastat loaded. So I'm going to go to add-ins, megastat. We're going to go to probability and we're going to go directly to normal distribution. Okay, and this is the interface that we're looking at when we click on the normal distribution. Okay, so let's actually put in the parameters of this normal distribution first before I forget. Remember, the mean was 30. Deviation we calculated for x bar, sigma x bar, was 0.5. Do not use the 2 that was for the population of individual scores. Now, and ignore the fact that it says x. We assume this is x bar for us because megastat cannot adjust its notation to different problems, or I should say different random variables. Okay, so I'm just going to type in for part C, we want greater than 31.25, so that's 31.25 seconds. And we want upper, right? Because it's greater than, so we want the upper. The axis label, I'm going to go with the original x bar in this case. Again, I know this is x, but remember, we know we're working with x bar. And pretty much that's it. Let's go transparent for the color or whatever you like and hit OK. And then megastat's going to create the output tab, and this is what the distribution looks like. So this is actually the shape is normal. The distribution has a center at 30 right here, mean 30, deviation 0.5. This is a z-score. So remember, 31.25 seconds, in other words, 31.25 seconds is 2.5. If you look at the z-score here, right in here, that the score of 31.25 is 2.5 standard deviation above. Okay, that's just if you want to translate it into a z-score. And probability of getting something at that value or higher is 0.0062. So we can, so the question says, what percentage of ads will take longer than 31.25 seconds? 62 in 10,000 ads take longer. So that's 0.0062, less than 1%. Remember, as a percent, this is 0.62%. Okay, I will write these in my notebook in a few moments. So there you have this one. Now let's do part D. For part D, let me go megastat, probability, normal distribution. Probability of greater than 28.25. Just type in 28.25 and do not, make sure the overlay is unchecked and hit OK. And there it is. Now greater than 28.25. Hold on. Yeah, that's fine. I was just checking because it looks like almost the whole thing. So deviation is a half, mean is 30. I'm just checking to make sure those did not change. They didn't. X is 28.25. Probability of upper means above that. That's above 28.25. Almost 100% of the ads are more than 28.25 seconds. So that answer is 0.998. Almost 100%. 2 in 10,000 lasts less than 28.25 seconds. Okay, now to do between 31.25 and 28.25, I'm going to go to megastat, probability, normal. Remember, for between, we do the larger number, the higher number first. That's 31.25. 0.25. Okay, and lower than that. I'm gonna go transparent and keep everything the same. Hit OK. And there it is. That's 31.25 less than. Notice this tiny region that's not shaded. So everything below it. But we don't want anything less than 28.25. So we're just gonna subtract 28.25 from it. Keep that overlaid now. Change that 28.25. Everything below 28.25 was extra. And change it to solid color. And you're going to see this part. 28.25 is actually down here. Way down here. Okay. And, okay, perfect. So the answer is going to be the difference between these two numbers, right? Again, below 31.25 is 2.5 deviation above. The 28.25 is negative 3.5 deviations below. It's way down here. That's why the number is so small. So I'm gonna actually do this by subtraction. Equal this number minus higher minus lower minus the lower. The answer is 0.9936. So I'm just gonna write it as 9938 minus 0.0002. That's 9936. When I go to my notebook, I can do that. And there we go. So we have the answer using Megastat. So I'm just going to pause this and then go back to my note. Very well. So I'm back here now. I'm just going to copy those numbers down that we found earlier in, what you call it, in Megastat. I'm just going to transpose those numbers into this. So for part C, the answer was 0.0062. 0.0062 or 0.62, not even 1%. The next number we found, probability of that was 0.9998. And for the between, what we did was we did the higher probability, 9938, minus the lower probability, and that gave us 0.9936. And there you have it, an example of working with central limit theorem. Okay, hopefully that's going to help you get through your homework. Your homework has problems very similar to this, so you should be able to formulate them. And with that, we are done with this chapter. And I want to make sure, yeah, everything looks good. So we're done. Thank you for your attention, and we are done.